In this video, I'm going to be reviewing the January 2026 Regents exam for Earth and Space Sciences. I'll be doing the first cluster of questions, which are questions 1 through 5. I'll start by reading this paragraph, highlighting it, so we can determine our answers down below. The Big Bang is a physical theory that describes how the universe expanded from an initial state of high density and high temperature. The theory attempts to explain how the universe has changed over time. Three pieces of evidence are used to support this theory. The measured amounts of elements in the universe supports the theory. The observed expansion of space that is accelerating is another piece of evidence. Also, the discovery of cosmic microwave background radiation supports the theory. The model below shows some information about how the universe has changed since the Big Bang event. Temperatures in the model are in Kelvin. Okay. So we can immediately see that it's getting colder. The universe becomes transparent, which is an important part. We can see that the cosmic microwave background radiation is coming 380,000 years into existence. The universe is transparent. And we'll go look at the questions and see what we can do. Complete each of the three statements below to correctly describe cosmic microwave background radiation by placing an X in the box to indicate which phrase correctly completes each statement. Statement 1. Cosmic microwave background radiation proves evidence of the Big Bang because it's energy and it's distributed throughout the universe, right? Because it spreads, as it says, because the universe is expanding. And the evidence is CMBR. So this one. And make sure to put an X and not a check mark, or else you'll lose points. Cosmic microwave background radiation is able to be detected because the universe, I just said that it cooled and then became transparent. So this is our answer. And statement 3 is telling us that cosmic microwave background radiation varies in the universe caused by density differences indicate that galaxies formed in areas of high density. Well, yeah, let's look at this picture. It's really dense. So these are our correct answers for question 1. Moving on to question 2. In the 1920s, astronomer Edwin Hubble studied galaxies using a type of star called a Cepheid variable. Never heard of that. These types of stars brighten and fade in a predictable pattern. Hubble observed these stars to determine how far away these stars and the galaxy in which they are located are from Earth. A reproduction of Hubble's 1929 graph is shown. Recessional velocity of a galaxy is plotted as a function of distance from Earth to the galaxies. It's measured in parsecs. Galaxies traveling toward the Earth have negative recessional velocities. So we're getting farther distance. And it seems to be in a mostly linear pattern as V is going up. Now, let's see the question. Several statements about Hubble's work related to the galaxies are listed below. Statement 1. Hubble's graph shows that there's no relationship between the distance of a galaxy from Earth and the galaxy's recessional velocity. We've already established that there was one. So anything with 1 is wrong. So that only leaves us with 2 and 4. Now, the strategy I like to do when doing these kinds of questions is seeing which answer they have different. These share the same answers except 5. So if 5 is wrong, or if 3 is wrong, then we'll know which one it is. So let's look at 3. Galaxies measured by Hubble that were 2 to the 10 to 202 million parsecs away from Earth all have a recessional velocity greater than 500 kilometers per second. Yeah, because they're all up here and it's above this line. So that's correct. And this does not have statement 3, so we can assume that this is the correct answer. How does the data in the graph support an explanation of the Big Bang Theory? Galaxies farther from Earth have greater recessional velocities, indicating an expanding universe. Yeah, that's right. But let's look at the others to see why they're wrong. Galaxies closer to Earth have negative recessional velocities, indicating that the rate of expansion of the universe only occurs around distant galaxies. It expands everywhere, so this is wrong. Galaxies located approximately 1 million parsecs away from Earth are traveling toward and away from Earth, indicating the universe does not expand further than this distance. It's always expanding, and it's still expanding right now. So that's wrong. Galaxies travel away from Earth at constant velocities, indicating that the universe is expanding at a constant rate. It's not at a constant rate. It is expanding, but it's not constant, so that's wrong. So our answer for 3 is 1. The table below shows some information about 2 stars in the Milky Way, Betelgeuse, and our Sun. Now, I'll immediately want to go to this page in the reference table, especially this part, so we can answer the question. Which statement correctly explains the difference in the elements composing the 2 stars and compares the lifespans of these 2 stars? In Betelgeuse, helium has fused into heavier elements, and Betelgeuse has a shorter lifespan than the Sun. I think this is right, but I'll just put a check mark there to see if any others could also be right. Yes, we know that helium has already fused into heavier elements like iron, according to this nucleosynthesis chart. And we can also see the lifespan here, as the stars that are using up more energy die earlier than our Sun, which is over here. So that could potentially be right. In Betelgeuse, hydrogen has yet to be fused from heavier elements. That's wrong because it's already at iron. In the Sun, heavier elements have completely fused into helium. No. We still have some hydrogen left, and the Sun has a shorter lifespan. That's wrong. The Sun will live longer. In the Sun, hydrogen has yet to be fused from heavier elements, and the Sun has a longer lifespan than Betelgeuse. Yeah, that's true. Hydrogen has not formed into heavier elements. Yeah, it did, because it... Wait, I'm wrong, because... Yeah, it did. It fused into helium. So this is wrong. So our answer is 1. Explain how the masses of Betelgeuse and the Sun are a factor in the rate of nucleosynthesis being different for each star. So, you're going to need to know a lot about how mass is a factor, or else you're going to get this wrong. So, the answer would be the greater the mass, the faster the rate of nucleosynthesis. And that's all I have to say. I know, my handwriting's terrible. But, as we can see here, the heavier the elements, the lifespan will be less for the star to remain. So the sun is still relatively young, and since Betelgeuse is larger, the rate of nucleosynthesis is faster. That's all you have to say. I'll do cluster 2, which are questions 6 through 9 in future videos.